Ladies and gentlemen, once again, I want to say a big welcome to all of you to the Valley of the Shadows of Advanced Quantitative Research. It's a pleasure to continue with a new area known as hypothesis testing. If you want to make your dreams come true, first you have to wake up, because you cannot make it true if you are still sleeping. You got to wake up. So what is hypothesis? And what are the steps in doing a hypothesis? A hypothesis is a claim, a conjecture about a population parameter. NDC will win the next election. NPP will win the next election. These are all claims. And who is making the claim matters. Whether the person is an authority or not an authority matters. Another person will try to debunk that claim, that statement. In the process of debunking the claim, you will have to go through some steps. And it is these steps that are known as the steps in hypothesis testing. They are basically 4 main steps in hypothesis testing. Step 1, identify the population parameter, which we call here as mu. Identifying the population parameter is the concept of what you are trying to discuss. So in the statement I made, NPP will win the next election. That statement of winning here is the parameter in question. Identify that. Then you formulate what is known as the null hypothesis, represented by H0, as well as the alternative hypothesis, represented by HA. The null hypothesis is the status quo. The alternative hypothesis is a mirror image of the status quo. The null hypothesis is the one that is supposed to be proven wrong, because it has stood the test of times. And because it's stood the test of times, your job is to disprove it. Once you have formulated the null and alternative hypothesis, you got to make a decision called a decision rule. You have to make this decision rule before you even start the analysis. So sometimes you see that in the papers, the person will add plus or minus. In other words, he assumes that there's going to be a positive relationship between something and something. So he brings a plus. Or he brings a minus. Because the decision is that we are going to have a negative relationship between something and something. Determine that decision rule ahead of time. And then you go to the next one, which is computing the test statistic. In fact, the computation of the test statistic is the most important aspect of the research. That one, you go through some rigorous mathematical combinations. If it is a software you are doing, the software will do that for you. But you got to know the mathematics behind the software, the statistics behind the software. Find the test statistic, compare the test statistic with a critical value. And the critical value, you will see that very soon. The critical value is the benchmark against which your test statistic is measured. The test statistic is the information that you have gathered that you are going to use to disprove the hypothesis. The information, the sample size, the observations, the individual means and the medians and whatever, those information you have collated, you come out with a statistic. And that statistic is measured against a critical value, a benchmark. And if the test statistic exceeds the critical value, you now have enough gravitas to reject the null hypothesis. But if the test statistic does not exceed the critical value, you don't have enough gravitas to reject the null hypothesis. Don't listen to what I'm saying alone. Write it down. So, apart from using the test statistic and the critical value, you can also use the p-value and the alpha. Now, the p-value is not the same as the alpha. Alpha is said to be the level of significance. The level of significance. It is also called the risks of drawing an incorrect conclusion. Let me break it down. You are about to check whether a statement that has been made is true or an existing statement is true, or a hypothesis, whether it is true or false, and your goal is to disprove it. And so you gather some facts and you try to come out with a story to debunk the idea. You are surely going to make some mistakes. You are allowed to make some mistakes. You allow a modicum of mistakes. The mistake you are expected to make is the alpha. So the alpha is the expected mistake you are making in your research analysis. That's the alpha. That is a level of significance. That is the risk of drawing an incorrect conclusion. And there are three main mistakes you are allowed to make. 1% mistake, 5% mistake, 10% mistake. You are allowed to make these mistakes. In other words, if the expected mistake is 1%, it means that you cannot make more than 1% mistake. If the alpha is 5%, you cannot make more than 5% mistake. If the alpha already chosen is 10%, then it means you cannot make more than 10% mistake. The lower the mistake you actually make is the p-value. So the p-value is the actual mistake, whereas the alpha is the expected mistake. Which one do you expect to be lower? The p-value is the actual mistake. Alpha is the expected mistake. Which one do you expect to be lower?
The p-value. The p-value.
The p-value. So when your p-value is smaller, you have enough gravitas to reject the null hypothesis. It doesn't matter which alpha has been selected. You have to find your own p-value, but you don't have to find the alpha. So even in the software, the default alpha is 5%. It's already given. Yours is to make sure that whatever p-value you get is going to be smaller than the default alpha. And then you can make conclusion. So the final step is to decide and then conclude. You got to make a decision and conclusion statistically first before you make it practically second. The statistical conclusion is important as well as the practical conclusion. In fact, the practical conclusion is the most important because at the end of the day, you're going to speak your result to management, to regulators, to legislators, to government parastatals. And so the connection between what you are doing and the statistical analysis you've done, that is critical. And the rule is very simple, that you reject the null hypothesis anytime the test statistic exceeds the critical value or is equal to the critical value, or anytime the actual error, which is a p-value, is less or equal to the alpha. Let's take a practical situation. Before you undertake a research, you got to determine the tail of the test. Yes, Obed.
Yeah. Hello, Doc. Please, I want to find out. You said the expected mistake for a research ranges from 0.1 to 0. From 1 to 10%. And I wanted to find out if it cuts across all industry, because there are some research that maybe the expected mistake might be higher than that range. So I wanted to find out if this is the benchmark, or there are some instances or some research where the expected mistake might be above that expected benchmark.
No. You see, the thing is that these are already statistical acceptance. This is expected mistake that you are allowed to make in a research. It doesn't matter which industry, it doesn't matter, as long as you are doing the research. These are there. So, and it's not based on industry. These are 3 different expected errors. And you are supposed to select the error before you start your research. So you're supposed to tell yourself that I'm going to allow myself this expected error. If you don't know what expected error you should do, I've told you the default is 5%. Now remember, you don't calculate this. You choose. You choose. But the p-value, you calculate. So you have to calculate the p-value. And when it comes to the alpha, you have to select. There are 3 of them. Does that make sense?
Yes, please. Thank you very much.
So you got to make a choice of what tail. There are symbols for the tail. Look at it carefully. Anytime, and these tail are based on the alternative hypothesis. Now, please note something before we continue. The null hypothesis, write this down. The null hypothesis always has some level of equality in it. For example, what is the opposite of greater than? You can tell us. What is the opposite of greater than?
Look, less than.
Less than is wrong. No. You can give me another answer. What is the opposite of greater than?
Less than or equals to.
You see, you are doing lottery here. So if one is not correct, one is wrong, one is not. Okay. So please be raising your hands. It will help me to, so that one person alone is not doing all the problem. The opposite of less than, greater than, is less or equal to. And the opposite of less than is greater or equal to. Because if you say that somebody is less than 30, its opposite cannot be he is greater than 30. Otherwise, you will not know the possibilities of where 30 will be placed. If you are less than 30, it means you can be 29, you can be 28. If you are greater than 30, you can be 31, 32. So where would 30 be? 30 must be part of the number line. So opposite of less than is not greater than 30, it's rather greater or equal to 30. The same way, opposite of not equal to is also equal to. Now, if you look at the alternative hypothesis, and these are usually the alternative hypothesis because they now has some level of equality in it. This one has some level of equality, the less or equal to. This one has some level of equality, less or equal to. This one has some level of equality. So that one is purely equal to. The alternative, which do not have some level of equality, they make up the alternative hypothesis. And with this alternative hypothesis, you can either have a one direction, like this too. One direction, because it's either you are greater than 30 or you're less than 10. So greater than 30 will be one direction. Less than 30 will be one direction. But not equal to 30 can be two directions. So that's what we mean by two-tailed test. The two-tailed test is a test where the alternative has greater than or less than, okay? Or better still, it has not equal to symbol. So not equal to symbol. And these are called two-tailed tests. So you can see that all the two-tailed tests will have not equal to. And that's a clue. And so once you write a null and write the alternative hypothesis, then you should be able to know whether it's a one-tailed or two-tailed. If it is this symbol you are using, it's one-tailed. If it is this symbol you are using, it's one-tailed. And the pictures of the two-tailed are also shown down here. Two-tailed means that you are looking at the right tail and the left tail. But one-tail means you are looking at only one side of the tail. So you got to know which tail you are dealing with, but it's only deductible from the alternative hypothesis. Next, remember we said that you should write your null and alternative hypothesis and then write your test statistic. Along the line, you will make some mistakes. There are some type 1 and type 2 errors you could make. The probability of rejecting a true null hypothesis is the type 1 error. You see, type 1 error is an error where you are rejecting a null hypothesis that is true. I'll give you examples very soon. The null itself is true, but you decided to reject it. That's type 1 error. And it is equal to the alpha. The type 2 error is where the null itself is false. But instead of rejecting it, you failed to reject it. You accepted a null, which is false. You have committed a type 2 error. Now, the others are not error. They are great decisions. For example, the 10 is false, you rejected it, which is a 1 minus the alpha. Okay. Or the 10 is true, and then you did not reject it. That is a good one. So the good ones are in the, right diagonals, while the bad ones are in the left diagonals. Got to know this. Now, why is this important? Because the kind of error you make will be as a result of the comparison between the alpha and the p-value you had. And that will determine the power of the test. You see, if you want your test to be very powerful, apply the central limit theorem. The central limit theorem says that as you are increasing the sample, your error diminishes. And over time, your value, your statistic approximates the true statistic. So a bigger sample size reduces the error and increases the power of the test. Now let's look at some type 1 and type 2 errors. What is the opposite of this statement? The null hypothesis says that the patient does not have cancer. What would be the alternative? What is the alternative to this statement? The null does not have, the patient doesn't have cancer. You can tell us. Papa.
The patient has cancer.
Good. The patient has cancer. Okay. Now, what do you think is the type 1 error here? What would be the false positive? Type 1 error from this statement. Remember, type 1 error is rejecting a true null hypothesis. It's true, but you're rejecting it. Francis.
Bro, the type 1 error will be that the doctor is saying the patient has cancer when actually the patient doesn't have cancer.
Guys, you get it? Okay. The patient doesn't have cancer, but the doctor says that the patient has got cancer. That is type 1 error. So there would have been an error committed in this contest. So there are several multiple choice questions on type 1 and type 2 error. I remember I used to do in those days. Okay, what will be the type 2 error here? What do you think will be the type 2 error in this statement? Error type 2. Yes, Papa.
So those one, the patient doesn't have cancer, but the patient, you are saying the patient has cancer, but then the patient doesn't have cancer.
Again.
The patient does have cancer, but the doctor says the patient doesn't.
Mm-hmm. Good. Okay. So that is called a false negative. Okay. The patient doesn't have cancer, but the doctor says the patient has got cancer. I hope that you guys were not copying, but you were saying it from your heart. Because when you're copying it from your notes, you struggle. Okay. Now, once you have decided on the hypothesis, you have to calculate your test statistic. So remember, first, you got to formulate your null and alternative hypothesis, which is what you see here. Then you have to go ahead and find your test statistic. The test statistic is given by mu minus x bar minus mu over the S divided by the standard, or all divided by the standard error. The standard error itself is the S over the square root of n. So you actually have x bar minus mu divided by the standard error, where the S is the standard deviation, the n is the sample size. Once you do that, this will give you the test statistic. Then you compare this test statistic with the critical value. If the test statistic exceeds critical value, hallelujah. If it doesn't, bad news. You can go ahead and reject or not reject the null hypothesis. Now, which test are we using? I'm using a t-test here, but you can equally use a z-test. When you use a z-test, when the sample is large enough, how large is large? When it is greater than 30 people or 30 observations. That is when we say that the sample is large. So that is it. Now, hypothesis. So all that we did was a one sample hypothesis. So the sample is just boom, one. You can easily do this in R. You can easily do this in Excel. In fact, when you watch my videos, you will notice that I've done one sample hypothesis, in Excel for you there. Okay. Just this week I posted that, so you can check. Now we are going to two sample hypothesis, and the hypothesis here is either going to be parametric or non-parametric. A parametric test is a test which assumes normality. A non-parametric test is a test which does not assume normality. So in a non-parametric test, the data is ordinal. It's ordinal. Okay, there are some outliers. It's truncated. So anytime you have ranking, you have to use non-parametric. And I see, in fact, some of the papers I'll give you, you will see that instead of them using non-parametric tests, they are using parametric tests. Punish them, punish those papers. So know the difference between parametric and non-parametric. We shall look at both of them. This is a two-sample situation. The advantage of the non-parametric is that they don't need the assumption of normality, because it's not all the time normality applies. Normality is very popular, but it doesn't apply all the time. So in non-parametric tests, we focus on the medians instead of the means. And they are outliers, so we allow that. If your level of measurement is nominal or ordinal, you can even use non-parametric tests for it. If your sample size is small, you can use non-parametric tests for it. But if your sample size is large enough, okay, then use parametric test, because that is the way to go. And then, of course, the data must be ratio or interval. So this is a table that shows parametric and non-parametric tests. Every parametric test has got its non-parametric equivalent. So who can tell me the non-parametric equivalent of the repeated measures of ANOVA? What is a non-parametric equivalent of the repeated ANOVA? What is a non-parametric equivalent? Can be okay, can be. Yes, Sewons.
So from the table is one-way repeated Friedman test.
Good. It's Friedman test, basically. You see that a paper is supposed to use Friedman test and you rather want to use ANOVA. Okay, so in two sample hypotheses, the principle is the same. Okay. First, decide on which test you want to use. Determine whether the data is dependent or independent. And then calculate the test statistic, calculate the Krecker value, compare the test statistic with the Krecker value, then you conclude. Or compare the p-value with the alpha, then you conclude. Remember, the p-value must be calculated. The alpha is already selected. But how do you calculate or how do you find the p-value? The p-value, if you are doing manually, you will find it from the table. Angie.
Good morning. Please, you said for the second step, you said check if the sample is dependent or independent. Please, what does that mean?
Okay. Who can help her? Who can help her with a dependent or independent sample? Who can explain to her? Emily, are you here? Who can explain dependent or independent sample? Okay, a dependent sample is a sample where the data is repeated. I'll give you two examples, then you can appreciate it better. So let's say that I take the scores of some students, okay, let's say 3 students of this advanced quantity. The first one had 51. The second one had 48%. The third one has 38%. These were their scores. Okay, the scores were not good. So they had to write again. And then I take, so this is their scores, first score, before. Then after they took a certain medication I gave them, I told them that they will get A. So in the score B, the same person here got 71. This guy got 81. And this guy got 91. Because the persons are the same person in this sample is the same subject that are being repeated in the next sample, it is said to be dependent sample. But suppose I take this person in the year 2003, their scores, and then I rather compare it with another sample, but they were in 2024. I'm comparing them now. Unlike the one before where I was comparing your own score with your own score. In this second scenario, where I am rather comparing your score with another separate person, because a sample is separate, it is said to be independent. Angie, does that make sense?
Yes, please, well understood.
So independent sample is where the subject is separate. Dependent is where the subject is the same. All right. Now,
Yeah, Doc, sorry, my internet was troubling me. If you can just repeat it for 1 minute, I'll be grateful, sir. Please,
okay,
please.
Angie, repeat it now for him.
So if you have a group of subjects and you administer a test the first time and you get some scores and you use the same subjects and administer a second test and get another score, then it is a dependent sample. But then if you are comparing scores of two different subjects, then the sample becomes independent.
Yeah. So these subjects can be human beings, it can be countries, it can be cars, it can be companies. So suppose you have the return on assets of 10 companies. And these companies are foreign banks. Then you compare the return on assets of these foreign banks and collect another sample. Okay. Let's say these are not even 10, they are 20, which are private, they are not foreign companies, but they are state companies. You're comparing the means of the return on assets. Because these samples are separate, the people and the companies are separate, we say that the sample is independent. But suppose you took the first sample and this same 10 companies, these 10 foreign companies, you took their return on assets in 2000 and compared their return on assets in 2000 with their return on assets in 2001. It's the same company. And because it's the same company, the sample is said to be dependent. Sometimes it's even called repeated on or matched sample. The repeated or matched sample, or related sample. Okay, now let's move on. In a two sample scenario, okay, not one sample we are done. You have to formulate a hypothesis like this. Look at it carefully. Then now for the population mean is said to be 1. So you calculate, the population mean is unknown. So when you are formulating the hypothesis, you are saying that, and this is a two-tailed testing. Oh, sorry, this is a one-tailed testing because of the alternative symbol. Okay, we went through that already. So you have mu1 less than or equal to mu2. The fact that you have mu1 less than or equal to mu2 means your samples are 2. Okay. But this is an indication that you are saying that the mean for the first sample is less than or at least equal to that of the second sample. That's what you're saying. This mean is not the X bar. It is a population mean, the unknown population mean. And then you now look at this second one, you look at the mean, you compare the mean, because this is going to be the opposite of that, it's just mu1. Look, this you can write it in a journal paper, in a thesis paper. So that's why I brought you the hypothesis and as well as the test statistic, because you can write it and submit it in your way. Okay, so once you have done the formulation, as we know, then you have to find the test statistic. But there are 2 ways. You see, you use the z-value if the sample size and the populations are known. They are known, okay, but most of the time we don't know them. Okay. But if they are known, then you use the z statistic here. Watch it. It's just the difference between the sample mean minus the difference between the population mean, all divided by the standard error of all of them. Now watch the standard error. It is just sigma. But in a situation where the population, the the samples, the population mean are unknown. So you see, the first one is known, the second one is unknown. When they are unknown and the sample size is greater than 30, so that is when the sample size is large, you use this formula. This is a formula that you use. The same thing, the sample difference minus the population difference, and just changing the sigma to S. So this is said to be the sample standard deviation, whereas this is population standard deviation. This is how you calculate a test statistic. But don't worry, if you're using a software, the software will do all of that for you easily. But you got to know what you're doing. That's a key. You have to know what you're doing. Next, what if you have a situation where the sample is small, which is normally what the situation is. And when we say small, less than 30, then in that case, you don't use Z, you use T. The same thing, the sample difference divided by the population minus the population difference divided by the standard error. And this standard error, the SP is the standard error for the sample, which you are going to find here. I think this mathematics is a bit missing, but it's actually N1 minus 1 multiplying the standard deviation of the first sample. Then N2 minus 2 multiplied by the standard deviation of the second sample. Then N1 plus N2 minus 2, the square root of all that. That's it. This will give you the test. So once you find this, you come and substitute it here, then you multiply it by what you see in the square root. Whatever value you get here is your test statistic. You compare that with this critical value. Okay. This is a critical value. And you read this manually from the table. Okay. But if you don't read it manually from the table, don't worry. The software will give it to you naturally by itself. Naturally by itself. So that is how you do this. That is exactly how you attach and tackle this one. Okay. Please, any questions so far? I know I'm teaching you theory, but it's very important to know the theory. Okay? The theories will help you. The theories are necessary. They will help you. Okay. All right. Now, let's go to the real deal. We are going to take our data and we are going to do all this in our data. So please open your MT-CAS data. I have mine here. This is my MT-CAS data. I want you to please open your MT-CAS data. Open the Excel of your MT-CAS data and also open your R Studio of it. This is my R Studio. I just need at least 3 people to be following me. Some people will not follow. It's all right. I like the challenge. Those who follow, I always like them. So in case you have forgotten, we called it data the last time. Okay. We called it data. Data. That was the name we gave to it. Look at that. And then let's load the data. So I'm just going to click, because I've already saved it. Just click data and then run. And you will see the data set here. You can see my, yeah. Let me run it again so that you can see it and let me show the first 7 variables. There you go. So this is my data set. Let me see by hands which ones have loaded their data. Those of you who have loaded the data. Let me see by hands. Good, good. That's incredible. That's quite an enormous number of people who are following me. Like I said, I needed at least 3. I've got more than even 8. Very good. Now, follow me. So what we are going to do now is we are going to, remember we always have a field of the data, right? Field of the data. Last time we generated contingency table. In case you've forgotten, this is a contingency table for some of them. But hey, let's move on straight to find it. Let me give you a bit about this data set. A little bit about this data set. So as you know already, this is the miles per gallon. This is a cylinder, displacement, horsepower, draft, the weight of a car, the kiosk, whether the car is automatic or manual. Okay. The VS. The VS is also dummy. Joseph, you have a question? All right. Then let's go to what we want to do. We are going to check. So the question is that determine if there is a statistically significant difference between the MPG of automatic cars versus that of manual cars. Okay. So in short, let's say you have your data and you have 2 samples. And now you have your data well arranged, and you want to submit your paper, your thesis. And you want to do a statistical analysis of the differences between automatic cars and manual cars. What is the first thing you have to do? Well, you have to generate some bit of descriptive statistics about automatic cars and manual cars. Oh, you don't see that. Let's do that. So let's get a bit of information between automatic cars and manual cars. And go to your Excel and look at the way we wrote it. We wrote it as AM. AM. So what I'm going to do is I'm going to go to the R, remembering that the name was AM. And then in the R, okay, if you can remember the last time, we used aggregate here to find a bit of the tabular analysis between automatic cars and manual cars. In fact, I'm going to use 2 things here. I'm going to use both contingency table to show you a bit about automatic cars and manual cars. So you can use this type table data, and this time I want to use just AM, automatic cars, and then I just want to use gear. Okay, I want to just compare the gearbox between automatic cars and manual cars. That's the first one. I just did that. Okay, so I use this one, and you can see that automatic cars, they have 15 of them have got gear 3. Okay, 15 of them have got gear 3. 4 of them have got gear 4. 4 of the automatic cars have gear 4. 15 have gear 3. Then the manual. 5 of the manual cars have got gear 5. And 8 of the manual cars have got gear 4. So it gives you a feel of the gears that these automatic and manual cars have got. So you can see that the manual cars have got higher gears. Do you see that? That's how you see they've got higher gears because they have gear 5 and gear 4. Okay, whereas majority of the automatic cars have got lower gears, gear 3. That's the first field. The second field is we want to list this, look at the mean, the descriptive statistics between manual and automatic by using this command. We have this command already. So let's start. I'm going to just generate the descriptors. Once you run this command, down here, you'll see it. Don't worry. So look here. You have for the MPG for automatic, look at it, it is 17.15. That is the MPG for automatic. And then the MPG for manual cars is 24.9. 6.39. Tapuyaya. So that tells you that the MPG for the manual cars is higher. Remember, you got to be so conversant with these R codes and have a feel of it. So watch it. The MPG for the manual cars are higher. Let's look at the standard deviation for that. Okay. That is a MPG. And in this case, I use the mean. Okay, I use the mean to do that. You can change this mean and use the standard deviation. Let me see what I do. Yeah, so this is the standard deviation. When you use SD, SD will give you the standard deviation. So when you use the standard deviation, you can see that the manual cars, the standard deviation is 6.17. The automatic cars, the standard deviation is 3.83. Okay. So you can see that the standard deviation is smaller than the mean. So it means that there's a lot of closeness. Most of the MPGs among the manual guys are closer to each other. And most of the MPG among the automatic cars are closer to each other. Anytime the standard deviation is lower than the mean, it means that there is not a lot of disparity. There is not much scattering. There's a lot of nucleation or closeness among the data set. So this is all to have a feel. This is all to have a feel of your data. You can even do a box plot between the manual and automatic cars and quickly have a feel of how they look like, a box plot. This was done last time by typing box plot MPG with a tilde sign AM and then give it a name. MPG grouped according to the type of car. Let's run that. Okay. Automatic. Yes, you have to change this AM and bring data dollar in front of it. The MPG to bring data dollar in front of it. Yes, Emmanuel.
Doc, sorry for this information. During my private text, I was using my second degree data to do the descriptive analysis with R. And even if I copied the MT card data and run it, my old private data still appears. Please, is there a way out?
The reason is because you called both of them data.
It's true. It's true. It's
So
true. It's true.
You have to just rename this one. You can you can simply call it MT cars.
Oh, okay. Then it will give me the feedback for the MT card. Okay, sir. Okay. So I've been struggling.
Or you can use your own name. You know where you normally will write data equal to read dot the length.
Okay.
You can just use your own name and say IMA equal to read dot the length.
Good.
And then,
then
once you keep using that word IMA, it will use what you have.
Oh, good, Doc. I've been struggling here, and now I'm okay. I can have my way out. Thank you, sir.
All right, so let's run the box plot. Okay, this is the box plot. When you do it, you can see it on the right here. Okay, that's a box plot for the data. And you can see clearly, just looking at the box plot, these are all before you do the work. You can see that the box plot is showing that the manual cars have got a higher MPG. You remember the descriptive statistics showed, and this time too, this one is showing they have a higher MPG than the automatic cars. Why? Because you can see clearly that the median is higher for the manual than for this. None of them have got outliers in the box plot. Now you are ready to do your test. Okay, you're ready to do the test. So let's go here. Yes, Samuel.
Yes, Doc. Please, does this the box plot indicate any skewness with that of the manual? Can we?
No,
ascertaining like
if there is
skewness.
any skewness, right now it doesn't. If there is any skewness, you see something like this at the top here, something like this at the top here, something like this at the top there, or something below at the down here, below the values, the upper values.
Okay.
I've seen it.
So please, why is just for understanding, why was the box, the line, as in the median line, there's much more, it seems there's much more values at the top, or maybe that will not be my understanding of the box plot. But then the
Well,
upper part is
the
larger.
median is this middle number.
Yes.
And this median here, above the median, you can see that a lot of the data are towards the 75th percentile. The upper value here is a 75th percentile. The lower value here is a 25th percentile. It appears that it is evenly distributed for the automatic cars. But what it means here is that majority of the data values are towards the higher upper echelon, the third quartiles, than in the second quartile, which is the median.
Yes, and that will not be described as a skew. That's what I want to understand.
Oh, well, we can check it. Okay? You can't use that really to discuss the skewness. If you want to use the skewness, the best way to use the skewness is to use the, what do you call it, the kernel density plot. That will be a better way to determine the skewness. So we can just do that. I think the last time we did kernel density plots. Okay, but you have to note that this one, it is a comparison. Okay, so you have to use a comparative kernel density plot, which I have in the code with the first lecture. I gave it to you guys. I can't go and bring that code here, but you can go and put it together. You will see whether it is highly skewed or not for manual. Try that, and then you can.
Thank you.
Yeah, you can.
Yes.
Tell us about that. All right. So, guys, what we need to do now is we need to estimate whether there's a statistically significant difference. Remember, these are independent. Automatic cars are not the same as manual cars. They are independent. They are separate. It's not the same thing. So, what test are you going to use? Are you going to use the dependent test or the independent test? Obviously, you're going to use the independent test. And when you look at the sample size, you would even know the descriptive parameters, okay, for each one of them. In fact, you can even do describe by group. Okay, let me just show you. So you can do this. I just typed describe, but I want to do this describe by. Describe by. Okay. So this describe by, then you type data dollar. I just want to try it. AM. Data dollar AM. And run it. Okay, so this one doesn't do. I think before you do that, you need to load the package called site. So let's load the package called site first. And then do describe by again. See. So still, let me confirm clearly the formula I'm using. Describe. Okay. Okay. So I can use this formula rather. Oops. I just want to show you a bit about this describe by. So you can have gen dollar data AM described by data. So do this, described by data, comma, data AM, okay? And that will give you a descriptive statistic for both of them. So watch it. I have the descriptive statistics for automatic cars here, and it tells you that 19 of the firms is the sample size for automatic cars. Then at the bottom, you have descriptive statistics for manual cars here. It tells you that 13 of the firms are manual cars. So you now know the sample size in each one. And of course, you know the mean in each one, the mean MPG, you know, the mean cylinders, the mean whatever for group. This is when you're doing a lot of group analysis. You can use describe by to separate the data set. Okay. Now, all of this, we've not even done our work. First of all, also check whether the data is normally distributed. You can easily check whether it's normally distributed, but I'm more interested in the T. So let's go to the T. We want to do the normal t-test. This is a t-test that has, remember, we've done the box plot already. Okay, I'll put data dollar in front of this because we have not attached the data. Data dollar in front of this because I've not attached the data. And just run your t-test. Now remember that this is going to give you the independent t-test, but it's going to be two-tail. Okay, two-tail. So you don't write anything. If it is one tail, you have to add the word alternative less to indicate that it's one tail, which means that the other one is going to be greater equal to. So let's see how the result is going to be. Powerful. It gives you the Welsh t-test. It's at the bottom. It's beautiful. It will tell you a lot of things. Okay, so let me see what it's telling you. First thing is that you have to write this in your thesis. Okay, this very one. T equals to, that's a T statistic, negative 3.7671. The degrees of freedom is 18.33. The p-value is 0, approximately. Okay. This is a two-sample hypothesis. It also tells you the mean for the automatic, okay, and then the mean for the manual. That is the mean MPG. Okay. Remember, we are testing whether the MPG is statistically different. Now, what does this tell you? First of all, look at the mean. The mean is telling you that the manual cars have got a higher mean MPG than the automatic cars. What does that tell you? Well, the fact that they've got a higher mean MPG doesn't mean that it is statistically higher. So to check whether it's statistically higher, go to the p-value. If the p-value is less than 5%, then it is statistically significantly higher. Now, if you look at a p-value, it's even more than 1%, right? 1% is 0.01. This thing is 0.001. So it's more than 1%. In fact, it is even closer to 0.1%. Okay. It's actually 0.13%. So it's even closer to 0.1%. So what does that tell you? It tells you that statistically speaking, not just the fact that it's bigger. It's bigger, but the difference is significant. There is a statistically significant difference in the mean MPG between the manual and the automatic. In other words, the manual cars outperform the automatic cars by a significant margin. That is how you look at it. If you like, do the one tail. We do the same thing. Okay, let's run the one tail. Okay. So let's go and pick this. Substitute to that. Remember that you should add the name of the data set to it and run it. Look at that. Okay, even one tail is better. The p-value is even more 0. Okay, the zeros are 3 before 1. Okay. So what does that tell you? It means that the manual cars highly outperform the automatic cars. This is going to be your conclusion. This conclusion is based on a statistical justification. So you put this information into your p-value, into your thesis, and then indicate this one and make that statement very, very buoyant. So that is how you do all of this. And of course, you got this result here in that regard. Everything that we did is all here. Now, the box plots that we did, the commenting about the box plots, no outliers, it was all indicated here. And I was telling you that you can check your kernel density plot. I did that here between the manual cars and automatic cars. You can check it here. So if you look at it carefully, the manual cars are the green. Okay, the automatic cars are the red. This tells you that the manual cars, the distribution of the manual cars are more towards bigger values. How do you know that? Because it appears that there's some sort of multimodality about the manual cars, and majority of the peak is towards bigger numbers, as you can see, than this automatic. Majority of the peak is rather towards smaller numbers. And you can see that this is wider. The manual cars, the figures are wider. The peak has a lot of wide values. And when you talk about outliers, to be honest, even though the data is not normally distributed by statistical justification that we did, all of it is not normally distributed. That is the NPG. We have not checked for the statistical outliers between the two. But you can see that the red one, the automatic one, appears to be much normally distributed, if you check it. Okay? And probably a little bit more outlying than the other one. But for me, there's not much indication of that significant outline. So that's how you can show the distribution. Okay? And you can see that the distribution of the automatic sits on top of that of the manual, but the manual stretches. Okay? So it has a wider distribution over the per gallon period. So that is how you are able to comment and then calculate your statistics in that format. Now remember, this was just assuming that these data are independent. And then you can do the test as we did, and you can find this result as we found. Very good. Any question on this before we go to the next one? Now let's go to the next. We are going to take this data set called HSB2, and I know you all have it. HSB2. In case you've forgotten where the data is, it is here. I sent it to you. This is the HSB2, the data set. Okay. Now, this has high school students. In fact, let me show you better. Okay. This is here. This is the HSB2 data set. I just want you to have a feel of all of this in terms of. So you have high school. Let me give you a bit of preamble. Okay. High school and beyond. So what you might call secondary school students. There are 200 students, secondary school students. And what you have there is the demographic of the students. So you have female, which shows the sex of the students. So whether the student is a male or female is all indicated here. This is a dummy variable. The next one is the race of the student. In fact, if you want a description of the data, is in the next Excel sheet. Okay, so race is Hispanic, Asian, African American, and then white. You see that here. So the first 6 guys are white. Then African American, Hispanic, another white, another African American, some white, and all of that. The socioeconomic status is the next column. You see, when the time somebody gives you a data, fill the data, know whatever is in there. You are in charge. You are in control of the data. Understand in total the data, the is, the all, the in, and the how. Okay. So some of the students are of low economic status, some are of middle economic status, some are of high economic status. The next one is a school type. Okay. Whether the student is going for the type of school of the student, whether the student is having a public school or a private school. So check it. You see that most of the white guys, so this is a white guy, and this white guy is in a private school. Another white guy is here, but he's also in what? In the private school. But it doesn't mean that all white guys are private school. You have these white guys who are also in public schools. Fill your data. What programs are the students doing? Some of them are doing general program, vocational program, academic program. So this is the main characteristics, the main features of the data. Now that we put them to exams, what were the score? The reading score of the student, the first student who was white, he was in a low economic status. He was in a public school and doing a general program. He scored 57 in reading score, 52 in writing score, 41 almost failed in mathematics, 47 in science, and then 57 in social studies. But compare that with a second person who was a female, also white, okay, of a middle class status, economic status, still in a public school, but was doing vocational, had 68 in reading score, 59 in writing score, 53 in mathematics, 63 in science, and 61 in social studies. So you now have a feel of your data. Let's go to the question. There's so many things you can check with. Okay. So question is, do males outperform females? In what? In writing score. Does the right score significantly differ across sex type? Okay. Does the right score significantly differ across sex type? Do males outperform females, or do females outperform males? That's the question. That's a problem of the day. How do you solve that? Well, this is another statistical work. Remember, who can tell me, is this question and the data, is it dependent or independent? You can tell us. Is it dependent or is independent? Can you guys hear me?
Yes, Doc, we can hear you.
Okay. So is it dependent or independent?
Doc is dependent.
Is dependent or is independent? Okay. Is this dependent or independent?
Hello?
Yes, I got it.
Okay.
Does the right score significantly differ across sex? Angie, are you here? Someone?
Doc, please, I'm here.
What do you say?
Doc.
What are your answers?
Doc, I believe it's independent since it's a single score being assessed.
Since it's a single score being assessed. That is not how we normally define independent sample. Look at the data, you can even see it. I mean, without even checking anything, you will notice that these are separate samples. We are talking about female, and we are talking about males. It's not the same person that we are checking their writing score. Males are different from females. We are checking the writing score. But suppose I was checking the writing score of males and I was comparing the writing score of males with their mass score. You see that thing? In that case, the same males, so I'm checking and comparing their writing score with their mathematics score. That makes that one dependent. Now this one, I have the females separate subject from males, another separate subject. And that makes the sample matched, related, dependent. Okay, so this is a clear dependent sample. And if it is a dependent sample, you have to use the dependent sample test or the t-test. But first, you can even have some feel of the data. Okay, so let's go here. To do this, you have to load the data. Okay, you have to load the data first. So the data is HSBT. So let's go and, okay, let's go and then load this data. Yeah. I just want to go down so that we all work together by loading this data. So I'm just going to go down here and just type HSB2. Oh, it appears the data is here. Oh. No. Okay, I have the data. I have. You don't have. Okay, so you guys should write HSB2 equal to read.delin. Okay. You are loading. You have to learn some of this thing. Read.delin equal to into bracket clipboard. And then load the data. So go to your data now after you type this. Click anywhere inside this. Do Control A to highlight, Control C to copy. Control A to highlight, Control C to copy. Come to your R where you have written the command and run it. Run it. After that, type head into bracket HSB2. We just want to show the head of the data. Okay, and that should give you something like this. Who are those who have been able to do this? Let me see the hands. Those who have been able to show the head of the data. Samson, well done. Well done, Sam. Who else?
Thank you, sir.
Well done, Manaf. Well done, Fosia Amy. Who else? I want to know those who have loaded the data. People that are hungry, they live a life of zero excuses. People that are hungry, they participate in their own rescue. They don't complain, they do it. Winners win. Losers lose. Full stop. No excuses. In the battle of success towards success, winning is the only hallmark. Okay. All right, so I've got enough people who have done that. So now you have loaded the data. Remember that our focus is basically to compare the writing score of male and female. That's all. We want to know whether females are better at writing than males or the other way around. So one of the first things you want to do is to do that group descriptive statistics. It's a very quick, easy one thing that you want to do. So let's go here. Okay. Sometimes I copy and edit some of the things. Yeah, Kingsley. So let's go here. Type describe by, and then type HSB2, then type comma, then type HSB2 again, and then type female, because that was a heading we gave to the sex type, female, just as I've done. Just as I've done. And run it. Okay, in my case, my HSB2 is not there, so let me load the data. Oh, hold on. I missed the typo. HSB2 is a typo, so always check typo. No grouping by female. Okay, so let's see the names I used. Female. Okay. Anyway, I didn't load the data, so let me load the data and be sure that this is what I'm using. HSB2. High school. So let me load the data here. Show the head of the data. And then, there you go. So if you do that, you should have a beautiful descriptive statistics across the sex type. So you can see from here. Yes, Samuel.
Prof, hey, look, sorry. Please, is it good practice to have the header of the column or one of the data attributes being the same label as the data content? So, for example, we have a column named female, and in that same column, there are female exists as some of the data points or some of the records.
Yeah, it's not a problem at all. Don't worry.
It's not a problem.
Yes.
Okay.
This is a data I collected from someone, and actually, it doesn't stop anything. So don't worry. That's a good question. We will not disturb it. All right, so you can see right from here, straight away, that the females are 109 out of the 200, and the males are 91 out of the 200. Quick descriptive statistics by grade. Number two, you will see that the females, the writing score, because that's what you're looking at. So you have to go to write. Okay, so this is a writing score. The mean writing score is 54.99. That is a writing score for a female. 54.99. What about the male? Well, the male writing score, is 50.12. So you have 50 and then you have 54. So basically the females have got a writing score of 55 and the male have got a writing score of 50. Now 50 is not that big from 55. The question is it big or it's not big? We don't know unless we subject it to statistical torture. So let's do that. But before we do that, let's have a feel of some few things. One, we can we can do, in fact, even a contingency table. Okay, you can do a contingency table for this. So you can just go here and we can look at the here. I'm just pasting and editing. If you look at the female here, I'm just going to take this one, copy this one, paste it here. We're going to compare the sex type vis-a-vis another categorical variable. And if you can remember, the other categorical variable was race. So one is see how many of the females are white, how many of them are this and that and that and that. Race is quite a lot. There are quite 4 races there. So that would be quite many, but let's still see. So let's type race and then type HSB2 here. Let's run that. So we can see the result. It's cool. It's still cool. Still cool. So look at the result. You can see that 13 of the females are African American. Okay, and 77 of the females are white. 7 of the females are African American. And 68 of the females are. Look, if you have not generated this contingency table, there is no way you can find this quick dynamics. It's a very, very good thing to always do. You only do contingency table across categorical variables. And you can do female as well as between females and the other socioeconomic status. You can do that. For example, you have socioeconomic status, you have school type. So you can even add a school type. If I add a school type, it's going to be complex, but it's good. Okay. You can go here, copy this, just edit and change the race, this time to school type. And you have to check how the school type was written. It was written like this. So you have to copy it from how it was written. It was written like this. So if you do school type, you're going to have this. So here, you will notice that this is interesting. Okay. So you will see that among the private schools, 13 of the private schools were females. 13 within the private schools, 13 of the females were white, and 14 were male. Okay. But when you go to the public schools, still you can see that 64 were white, and then for the male, 54 were white. So you have I like the Hispanic section. Look at the Hispanic section. Among the public schools, 13 of the male were Hispanic. Okay. And no male was Hispanic among the private schools. No male was Hispanic. So again, it gives you a feel that these Hispanic boys, are not going to school at all in the private schools. The Hispanic boys have become truant, cubolos in the private schools. Most of them are in the public school because it is a banned school. But the females are a little bit disciplined. So few of the female Hispanic students are in the private schools.
Doc, is it not also possible they don't have the cash to go to the private schools?
It's possible. It's possible. Anything is possible. But the good thing is that you tend to see a lot of dynamics using contingency table. You wouldn't have seen this if you have not done that. Okay, so that is another thing you can do. And now the next thing you can do is that you can generate a box plot of the data. How do you do that? Well, I'm not going to give a title. I'm just going to take this one and run it here. So I'm going to do a box plot of the data set, okay, just like this. But a box plot of what? Remember, we are doing right. So I'll do right. Okay. And then across female or across sex type. I don't want to give a title, none of these things. I'm not going to give any of those. Okay. Let me just remove all of it. And then just have this box plot. Let's see if I do color equals to 28, something of color will show. Do what I'm doing. Let's do what I'm doing. Okay, so that's it. You see, it has given me some beautiful box plot. It's giving me some nice color. And you have females, guys, you can see clearly that the females are leading in terms of writing score, just graphically. And then in terms of the males are losing in terms of median in the writing score. Okay, so at least once again, this confirms what we saw in the descriptive statistics. You can now go ahead and remember, this test is purely an independent t-test. We are going to do two samples. We're going to do two tail tests. And remember, two tail test captures also one tail. So we are just going to do two tail tests. I'll just copy this and change the names. Okay, so just use HSB2 right. HSB2 right. And then on this side, you use female. You use female. This is a t-test that we are trying to. The evidence will all be clear here. Everything will be clear. Everything will be clear. I mean, it would have been nice, to be honest with you. Let me see what I can do that. It would have been nice to check whether the data is normally distributed. The thing is that you have to do it because the data is already scattered. Okay, you can check. Before we do this, you can check whether right alone is normally distributed. Okay. So let's just do it here. Shapiro dot test HSB2 right. Okay. So this, let me put an instruction here and say check if writing score is normally distributed. Check if writing score is normally distributed. So let's run this. And there you go. Look at the p-value. Remember, for normality, we are told normally when the p-value is rather bigger than 5%, that is when it's normal. Now here, it shows that it's not normally distributed. So it means that t-test might not be appropriate because t-test is for normally distributed data. Having said that, though, let's check the kernel density plot. Let's just do a kernel density plot and see whether that is true. In fact, I want to do the kernel density plot before I did that. So let's give it a title, plot KDE plot of right. Okay, scatter plot of right. And let's change this to am I having what I thought I'm having? Hold on. See. So let's take this. Just follow what I'm doing. Okay. So let's do right we just want to check graphically. And then we change this one to, so plot density HSB2, right? The line width is 4, the color is red. The Rutiger jitter is the same as HSB2 data. We just run. Good. So you can see why it said that it's not normally distributed. Okay. The result, and this is a Shapiro test, is way below 5%, which means it's not normally distributed. And now you can see it doesn't look normally distributed at all. All the same, we're going to run our t-test first. And this is a command for the t-test. HSB2 dollar, right? Tell the sign HSB2 dollar female. Okay. Run that. There you go. There you go. Of course, you will always have to compare a non-parametric test and add a parametric test to it. Okay. This is not normally distributed, but we are not, I mean, you guys know that scores are 100%, you know that. So anytime something is in percentages, it is not usually normally distributed, generally. Okay. And that is why this appears to be not generally distributed, because it's even truncated at 1 from below, and then at 0 from above. All right. So you can see from here clearly that males are truly bigger in terms of writing score than females. Now check the p-value. The p-value clearly shows that the difference is significant. Okay, there's a statistically significant difference between male and female scores. And so you have to take this t-statistic degrees of freedom p-value result, match that against these mean scores, take it to your thesis paper or your document, and then make a writable conclusion. So what does that mean? It means that using this parametric test, okay, just based on this parametric test, we can conclude without a shadow of a doubt that females outperform males when it comes to writing. Okay? When it comes to writing, the females are excellent. Statistically speaking, they are significantly outperforming the males in all respect, because this has a statistical backing. Now, the non-parametric analog of this parametric t-test, which is also called Welsh two-sample test. Okay? So this is, in case you haven't seen it here, okay, this is independent. Yes, and this independent test is called Welsh. Its non-parametric analog is known as Mann-Whitney. Mann-Whitney. Now, when you go to the slides, okay, Mann-Whitney is there, but we'll do that next time. Okay. When you go to the slide, okay, you will see something known as Mann-Whitney. And in fact, we'll come and do the same thing, this one, okay, for that same Mann-Whitney. It is called Mann-Whitney U-test. Sometimes it's called Wilcoxon sign rank test. I'm just going to do it here, you know, just as a comparative analysis. So please, the name is called Wilcox. So when you type Wilcox, okay, it will pop if you have an internet. Wilcox.test. Wilcox.test. And then you can do everything that you did here. Just double check. There's that. You can just copy everything that you did from here into the bracket down there. Okay, so this is Wilcox.test. It is the non-parametric analog. Okay, which is called Mann-Whitney U test or Wilcoxon, and there are two of the Wilcoxon, so you got to be careful there. Wilcoxon rank sum. This one is called rank sum. not sum rank, signed rank, but rank sum test. So this is a Wilcoxon rank. You see, I'm putting some instruction here with a hash symbol. It always helps you to know. So this is a test. Remember, we decided to use this test instead of the t-test because we realize that the data is not normally distributed. And when the data is not normally distributed, non-parametric test is the way to go and not the parametric test. But even when you use a non-parametric test, support it with the parametric test because parametrics is powerful. So let's run that. And when you run that again, you can see that it is also, significant. It also shows clearly that there is the p-value is 0. So there's a clear significant difference between the score for the male and the score for the female. You see, one slight disadvantage of this Wilcoxon rank sum test is that it gives you the Wilcox text statistic, but it doesn't give you the mean. So that's why it's even nicer to run the t-test, because the t-test will automatically give you the mean for each one. Before it gives you the score, it also gives you the mean. And the t-test also gives you the confidence interval. Okay. And normally the test statistic must fall within the confidence interval. You see the confidence interval is 2.24 up to 7.5. And the t-test is 3.66, which means it is falling within. It's falling within. And that is the way we go. So clearly, both tests are showing that the men are underperforming the female. Significantly speaking, statistically speaking, the men are underperforming the female. Any question on this? Any question? Okay. So everything that we did is here, so you can check it. Okay. And so the conclusion is that this is how you write a conclusion. The results indicate that there is a statistically significant difference between the mean writing score for males and females. You see, you have put the T and P values there. In other words, females have a statistically significantly higher mean score. You write the mean score than males. Females generally outsmart males when it comes to writing. That last sentence shows you have a full understanding. Okay? So what this means is that if you are looking for people to give scholarships to, when it comes to writing for this group, you got to start, encourage females to apply, because they might think that the men do better than them probably in maths. And so because the men do better than them in maths, they will think that they do better than them in English, in writing, which is not really the case. You can come out with policies, educational policies, because you understand the score. Now, that is when the sample size is dependent. When the sample is dependent. But when the sample is independent. But when the sample is dependent, Emily, we now come to your point. When it is dependent, it means that in this case, you cannot use the t-test independent. You have to use the t-test dependent. And this is a test statistic for that. The test statistic is in such a way that you are looking at the differences between the before values, because remember they are dependent, the before values and after values. So let's say that I have an example here. So the D here is looking at the difference between the before and then the after values. The D bar is the mean of the difference you would have calculated for each individual. For each individual, before value, after value, before value, after value, you find the difference. You find the difference. You find the difference. And then you sum the difference divided by the sample size. That will give you the mean. Then you take that mean, then you divide it by the standard error. The standard error is basically the standard deviation divided by the square root of n. The full standard error is this. The software calculates all of that. But always remember that whenever it comes to these samples, the data must be normal. You have said that many, many times. So there's a quick example of two people who are being graded. I mean, two examiners. Okay. So you have two examiners. They are facing a dilemma of a certain group of students. Okay. And they want fairness. These students have said that their results are not good. They said that their results are not good. So we go to grader 1, and then he scored these people. And then grader 2 takes the same paper and scores them as well. Okay. So there are a bit of differences between the scores. So what the t-test, this data is supposed to be normally distributed. And if it is, what the t-test does, the paired t-test, the dependent t-test, what it does is to calculate the differences and then calculate the mean of the differences, and then calculate the standard error and find the test statistic and the p-value. Compare that with the critical value and the alpha. If you check this carefully. And how do you write this? Look at it. If you use this formula in R, and then you go and run it for our own, it will not work. Look at what it will say. I'm going to do the same thing. So instead of running the independent t-test, suppose I have run the dependent. And here, I would have chosen the same right here. Okay, the same right here. And then the same female here. Female here. And of course, I would have brought the tilde sign. Oops. I would have brought this tilde sign. And then you add the word comma paired, true. Paired, true. So that will show that you are running a paired t-test, dependent. Watch the result. It will tell you that the method cannot use paired in the formula. Okay. The reason why it's telling you this is because the data is not paired. Remember, one was 109, the other was 91. You see, for the paired to be used, they must all have the same number. 109, 109, 100, 100, 250, 250. That is paired. So for the paired, it must be arranged in that form. So what can you do? Which of the analysis can be done? Well, one of them that can be done is comparing the writing score and the reading score. So here I can rather change it to read because you are paired. Okay? So I'm comparing the writing score and the reading score of all the 200 students. And watch this. Oh, hold on. It also says the writing score and the reading score. Okay, I need to arrange them. I need to arrange them so that we know clearly these individuals. First of all, let me just quickly remind myself of this. You're comparing the writing score and the reading score of these. So they have to be arranged. So you have to be arranged by type. So if it is by type, they must have the same type in that vertical order, not in the same horizontal ordering section. Okay. So it will not naturally work. You have to arrange them like 100 starting and then another 100 following downwards. Then it will now work perfectly. Other than that, in this very fraction, it will work. So Either that way or you type them like this. You type them this way. But don't worry. Next week, I'm going to look at the non-parametric version of this, and you'll see that. So this is how you run, and then just add paired. If you do paired true, that means you are dealing with dependent sample. If you do paired false, it will take you, it's like doing back the independent that we did. Okay. Now the Mann-Whitney, I've spoken about it already, assuming that the data is paired, is independent. So this is a Mann-Whitney, which I did already, which the data is independent. We did this some few minutes ago. And this is a non-parametric version of the Mann-Whitney U-test, also called Wilcoxon rank sum test. This is the non-parametric. So remember, the Mann-Whitney U-test is the same as the Wilcoxon rank sum. But this one is Wilcoxon signed rank, which is the dependent version. So the paired version of the t-test, which is paired, is called Wilcoxon signed rank. Don't confuse yourself with the Wilcoxon rank sum. There's a difference between Wilcoxon rank sum and Wilcoxon signed rank. Signed rank and rank sum are both non-parametric, but rank sum is independent, signed rank is dependent. So this is it. This is a command. Okay, so this is the way it should have rather been written, actually. So watch this. So if I go back here and rather replace this one, you can check it with yours. Wilcox.test, write and read, but choose pair. Okay, choose pair. But I think this was the same thing I did, isn't it? Okay. Of course, this one is not going to work because it's not numeric. So I need to attach, it's supposed to be a comma. It's supposed to be a comma. I didn't mean add pair. And then add pair equal to true. Okay. Do a comma. Yeah. So watch it. HSB2 $write, HSB2 read. It's supposed to be read. Then pair true. So watch this. This will give you the paired result. And you can see that clearly. Okay? The p-value is 36%, way higher than 5%, which means, this is interesting, because what this means is that there is no significant difference in the reading and the writing score of all the students. The students are doing quite well when it comes to reading and writing. There is no significant difference. They don't outperform. Reading doesn't outperform. They don't outperform any other, okay, in terms of reading and writing score. Now, we assume that this data was non-parametric. We assumed it was non-parametric, but I got to check whether it was non-parametric first. First of all, we can check that the write was non-parametric. We did that here. Okay. You can check whether the reading is also non-parametric by doing plot, blah, blah, blah. Instead of write, you do read. And when you do read, you get this graph. You see, reading is also looking non-parametric. It's not that normally distributed. So we can go ahead and do the Wilcoxon, which we did, which shows that there is no significant difference. So get to know, they are a little bit confusing, parametric, non-parametric, parametric, non-parametric, they're a bit non-confusing. I go through it and solve all of this. Now, I have an assignment for all of you to do and submit, and you're submitting this assignment in a week's time. It's a week today. One, you have this, you're supposed to determine what is parametric, non-parametric, and solve. Is there enough evidence to solve this and conclude using R? Then you have, assume you send your salesperson, solve this as well. And assignment 3, a new therapy has been produced, solve this as well. Okay. Write a null and alternative hypothesis for this. And that is all. So 3 assignments. This is your first assignment, and you have a week to submit this assignment to me. Ladies and gentlemen, that brings us to the end of the entire caboodle for this. At this stage, you may have some questions, please. I'm all ears. If you have a question, let it flow. Let it flow.